This is Mr. Nakauchi hitting our final topic, new topic of the year, and that is going to be evaluating limits, which we've seen before. Now they're to infinity. It's not always just a number here. You can evaluate things to infinity. And in this case, I asked you to evaluate the limit as x goes to infinity of x squared. Now, when you have this, if this is luckily a pretty simple equation that in our brain, we could just kind of sketch that out. All right, x squared is just a parabola, right? And as x goes to infinity, right, that's actually an inherent positive infinity. So that means what's happening as this graph goes to the right. And of course, as you go to the right, it's going up and up forever. And it never really stops at any particular number. Like whatever number we pick, it's just going to keep going. As you go to the right, the graph just gets bigger and bigger and bigger. So the short answer of this is that the limit for this does not exist, all right? Because a limit has to kind of stop at a particular number for it to exist, or there has to be a particular spot. And you can't just, if you plug infinity in there, you just get bigger and bigger numbers. The bigger number you plug in, the bigger number you get, and there's no limit to it. So I would just say that the limit does not exist. Now, depending on other resources, some books would say since you're going up forever, these are all positive numbers, infinity. So some books would call that positive infinity, and that's totally fine, but we're going to stick with this as an answer just for simplicity's sake. But if you do see some books call it positive infinity, and they put positive infinity here, that is an option. All right, but we're just going to deal with infinity always being positive here. It is also possible to put in a negative infinity, meaning you're going to the left. We are not going to deal with that in this class. We can save that for another class or in college or pre-calculus, whatever. We're only going to deal with positive infinity. So I'm going to not always write that plus. It's just implied that we're only going to do positive infinities. And in our case, for x squared, it does not exist. Okay? And it's not going to exist for most graphs, all right? If I said divide the limit as x goes to infinity of the line, say, x plus 1, that's just a line. After you graph the line x plus 1, you go there and the slope is 1. And that's actually kind of the same deal. It doesn't really seem to stop anywhere. So that limit also does not exist as we put it. All right, so that's that. So a lot of the, whoops, limit to infinity, I didn't draw that, right? Many of these limits to infinity in real life tend to not exist, right, in general. But there are exceptions, all right? So while most graphs go to infinity and don't exist when you do that, there are some notable exceptions. And of course, in math, we're kind of fascinated by the exceptions to the rule. So one of the main exceptions is if we evaluate the limit as x goes to infinity of the graph 1 over x. And this small example is going to turn out to be a really big deal. All right, so let's kind of mentally graph the equation 1 over x. Now that's what we know as a rational graph. It has an asymptote, a vertical, excuse me, a horizontal asymptote, and the graph kind of goes like this, right? Remember these graphs? It's called a rational graph, 1 over x, right? Now this time, as the graph goes over to infinity, the graph doesn't just get bigger and bigger and bigger forever. It gets closer and closer to a particular number in the y-axis. And in the y-axis, the number you're getting really close to is 0. Right? This number, but when the graph is going close to an asymptote, the limit as you go to infinity, of course, it depends on the graph. In this case, it's going to get close to 0. So this limit actually equals 0. It does exist because the number you're getting really close to is infinity. Remember, the limit is not an exact number. It says what number are you getting close to as you go on and on to the right forever. And we're getting really close. The y values are getting really, really close to 0. Here, the y values don't get close to anything. They just get big forever. But here, the y values get very close to 0. And this small one, seemingly like random example, is actually going to be the basis for a lot of our equations. Kind of like really remember that one, because we can apply that to a lot of situations. Because it turns out that anything that even has an x in the denominator, for the most part, is going to equal 0. Meaning, if I should find a limit as x, when it going to infinity, of course, we are only talking about examples where they go to infinity, with a limit goes to infinity. Because if it's another number, it will apply to the previous lesson we did. But when x goes to infinity, I want to find 1 over x squared. Here's what I would do. Basically, 1 over x squared is really just 1 over x times 1 over x. I already know 1 over x goes to 0. So this limit is like 0 times 0, which is also 0. So the limit of 1 over x squared is also 0. And you could do the same thing for the limit as x goes to infinity over 1 over x cubed. That's going to go to 0. 1 over x to the fourth, 1 over x to the fifth. 1 over x to any power is going to turn out to go to 0 because they're all the same. If you graph that, this side doesn't look different, but this side still goes to 0. All right, so that's kind of a general rule that the limit as x goes to infinity of 1 over x to any exponent, right? It could be any exponent, 1 over x squared and 1 over x to the cubed, x to the fourth, 1 over x to the fifth, or even just 1 over x to the first. If a is 1, that's that one. That's always going to equal 0, okay? And believe it or not, it doesn't have to just be a 1 there. Okay, another example I'm going to share with you is perhaps this one. What if you had to, and all these are just evaluating, you evaluate the limit as x goes to infinity. Again, we're only doing infinite limits for this video, right? Of say 3 over x. Now you have to answer, does 3 change anything? And well, that's 3 over x is like 3 times 1 over x. And this limit is going to be in 0, so it's kind of like limit of 3 times 0, and that's still going to be 0. So no, this 3 has nothing to do with it. This limit is still going to be 0, okay? So I'm splitting 3 over x is 3 times 1 over x, and then plug in, right, when you want to plug in infinity limit, you plug that in, and when you plug in 1 over infinity, you basically get 0, and 0 times 3 is still 0. So even if you have another number there, even if the number had been in the 0, the limit as x approaches infinity of, say, 5 over 2x cubed, right? Well, here's what you do, kind of split that up into parts mentally, and that's like 5 times 1/2 times 1 over x cubed, all right? That's a 5, all right? Because that's like 5 over 1. So it's 5 over 1, or just 5 times 1/2, right? That's 1/2 times x cubed. And then plug in your infinity. Now, there's nothing to plug in here. That's just 5. 1/2 is that. And 1 over, when you plug infinity over 1 over x cubed, that becomes 0. And 5 times 1/2 times 0 is just 0. Your final answer is 0. So the point is, it doesn't, the shortcut is, it doesn't even matter if there's numbers on top or bottom. If there's an x in the bottom of a fraction, the limit becomes 0. That's it. And that part of the limit becomes 0. Now, another example, let's find the limit of x going to infinity of this function, or maybe it's like 5 over x to the third plus 3 over x squared minus 7 over x plus 2. Find that limit. Now, at first you're probably thinking, well, this is insane. I don't know how to do this, but let's think about this. There's 4 parts to this. Just take each part one at a time. And this part is going to equal, when you plug in the limit, 0 because there's an x in the bottom, plus this part, and when you plug in, there's an x in the bottom and it's going to infinity, that part is going to become 0. And then minus, and then this part has an x in the bottom, so that part is going to be 0. Plus, now this part doesn't have an x in the bottom, and in fact, there's nothing to plug in, there's no x, so it's just 2. And then just work that out. 0 plus 0 minus 0 plus 2 is going to equal 2. The limit of this is just 2, because basically, anything with a x to any exponent on the bottom of the fraction, all those parts just become 0. So it actually just reduces pretty quickly. So anything that looks really complicated like that, all the parts that have x's in the bottom of the fraction just become a 0. End of story. That's it. And anything that doesn't sticks around, right? And that's what you do, okay? So now, again, this doesn't get you out of everything, but we're only going to kind of give you specific problems where these rules apply. Now, the ones that don't apply, we're just not going to get into those. That's kind of a whole nother issue. But all the problems we're going to give you are either like what we did earlier, or like these, and these categories, or like these, these ones, they didn't have x in the bottom, so there just does not exist. If x is in the bottom, for the most part, it doesn't exist. And if x is in the bottom, it just equals 0. And if there's parts of x in the bottom, it still equals 0. And the parts that don't have x in the bottom just stay put, okay? Now, so that will kind of get you through it. And using that rule will kind of get you through problems like this. Let's not worry about this one right now. Now let's evaluate this one. Now this one's a little more complicated, all right, because we have a lot of stuff there. But what we're going to do is we're going to use a trick, all right? So to evaluate this limit to infinity of all this, it's not just going to all be, well, this is all 0 because there's x's in the bottom. The problem is there's a mix. It's x squared. They're not kind of like independent fractions like they were before. So in this case, we just have to use a trick. And this is the trick that's going to get you through most of your homework, all right? And the trick is, look, so I'm going to write this in purple. Look, I don't know if you can see that color, but that is purple. Look for the highest exponent. And in this problem, the highest exponent is 2, x squared. X squared is the highest exponent. There are 6 pieces to this problem, 3 terms in the top, and 3 terms in the bottom. So 3 plus 3 gets me 6 terms altogether. Look for the highest exponent in all of them. The highest exponent is 2. There's 2 of them with 2, and that's the highest exponent. Right? So now the trick is I'm going to divide all terms by that highest exponent. Right? So this term, so technically I'm finding the limit. I'm still finding the limit as x goes to infinity. Because here's the thing, you can do anything you want to a term as long as you do it to everything fairly, right? Like if I give the class, if I give one person $1, that's not fair. But I give everyone $1, everyone should be happy because everyone got the same amount, right? If I take $1 away from everybody, that's not very nice, but at least I'm being fair because I'm doing it to everybody. So math is the same thing. You can do anything you want. If I want to give everyone $50, I could do it. As long as I do it to everyone in the class, I think everyone would be happy. If I said everyone give me $20, I think a lot of people would complain, but hey, if I did it to everyone, technically it's still fair, although you would have a right to complain. But technically it's fair if I just do it to everyone. So here, take all these terms, and the highest exponent is x squared. So I'm going to take 2x squared and divide it by x squared, plus 3x divided by x squared, plus 1 and divide it by x squared, all over 3x squared minus 5x plus 2. But I can't take these and divide them by x squared and x squared and x squared. I'm going to divide everything by the highest exponent. Now, you're freaking like, why? That makes everything so complicated. It looks it, but watch. Things simplify pretty quick. 2x squared over x squared is just 2, because these cancel. 3x over x squared is just 3x. And then 1 over x squared just does stay 1 over x squared. All over, and then x squared over x squared, those cancel, and you just get 3, minus 5x over x. The x's cancel, so you get minus 5x. And then plus, and then this one doesn't reduce at all, so 2 over x squared. And I'm like, okay, well, that's a little better, but that's still kind of complicated. But then here's the thing. Use that rule that I said earlier, that the limit of x going to infinity of 1 over x equals 0. What that tells you, this little rule tells you that anything with x in the bottom goes to 0. And so this part becomes 0. It goes away. This part becomes 0. It goes away. This part becomes 0. It goes away. And this part becomes 0 and it goes away. The only parts that didn't have 0 was 2 on the top and 3 on the bottom. So that's just the fraction 2/3, and that's my answer, right? That is the limit to this as it goes to infinity, right? The limit is 2/3. Okay, so I divided everything by the highest exponent, and then when I do that, now, why? Someone's like, how come I never did this trick before? Because you can only do this trick if you're doing a limit to infinity, right? So once you divide everything by the highest exponent, all the terms that have an x in the bottom just becomes 0. They all became 0 and disappeared. What I did was 2 plus 0 plus 0. Well, that's just 2. 3 minus 0 plus 0, that's just 3. Right, so they all become 0, and essentially just vanish. That's why I just crossed them off. They're 0. Who cares? They don't even need to be there. So divide them, and so then all terms with an x on the bottom, or anything that's like 1 over x, or 1 over x squared, or even if it's just a number. This is 3 over x. Who cares? Still goes to 0. 1 over x goes to 0. 5 over x still goes to 0. Okay, it doesn't even have to be a 1. Right? They all turn into zeros. All right, so 1 over x, and it could be any exponent. 1 over x squared, 5, they all go to 0. Okay, so we're going to try to do this limit here of x going to infinity of x squared minus 9x plus 1, that is a plus 1, over 3x cubed minus 2x minus 15. All right, now let's follow our same steps before. The highest exponent is 3. So I'm going to take all these terms, the x squared minus 9x plus 1. And I'm just writing the whole thing, so you can kind of see, minus 2x minus 15. Okay, take all those terms and divide them all by the highest exponent, which is x cubed. And then let's simplify what we've got. X squared over x cubed. I'm going to write this in the next step. I'm still doing the limit. You can write it if you want, or you can just kind of remember. Right? X squared over x cubed is going to be 1 over x. And that's going to be minus 9 over x squared, right, when you reduce, plus 1 over x cubed, okay, all over 3, because right, these cancel, x cubed over x cubed, just cancels, minus 2 over x squared, minus 15 over x cubed. All right, so that's everything we've got so far. Now remember, since I'm doing the limit to 0, out of these 6 parts, any part that has an x in the bottom becomes a 0. So this becomes 0, that becomes 0, that does, that does, that does. The 3 does not, because it doesn't have an arrow. X in the bottom, so that stays put. So I have 0 minus 0 plus 0 over 3 minus 0 minus 0. Simplify, you get 0 over 3. Now what does 0 over 3 reduce to? 0. And that's perfectly fine. Remember, I said it's fine to have zeros on the top. You just can't have zeros on the bottom. Okay, so a limit to infinity can equal 0. Right? That's just, it's as we said, limits of 1 over x is just 0. A limit of a bigger function can also equal 0. All right, final example we're going to do is this one. All right, they're all lines. You can see the limits of infinity of this. This one does not have 6 terms, and that's okay. Kind of all works the same way. Find the highest exponent. In this case, the highest exponent is 2. All right, rewrite it. 2x plus 9, x squared plus 9 over 5x plus 2x squared minus 3, and divide everything by the highest exponent. That's x squared. All right, let's simplify what we've got. X squared over x squared, I'm going to squeeze the answer here, is just 1. And then 9 over x squared doesn't simplify. 5x over x squared becomes 5 over x. 2x squared over x squared, these x squared just cancel, and I'm just going to get 2. And then minus 3 over x squared doesn't simplify. Okay, whoops, you can't quite see that, but now you can see it. Okay, all right, so that's what we get. All I did was simplify this, right? That became 1. Right, so that's kind of how we got all this. Okay, now remember what I said, anything with an x in the bottom, because we're doing a limit to infinity, anything with an x in the bottom becomes 0. So this is 0, that's 0, that's 0. The 1 and 2 are not, so I got 1 plus 0 over 0 plus 2 minus 0. That's just 1 over 2, and that doesn't even reduce, so that's my limit, 1/2. So you can get a wide variety of answers. You can get numbers, you can get do not exist, right? So the big thing is to remember this rule right here, right? Which I'll move up a little bit in the box, right? First, look for the highest exponent. Second step, that's first step, divide all terms by that highest exponent. And the third step is that all terms with any kind of x in the bottom just become a 0, and you simplify whatever's left. Okay, so that's your final video lesson from me for the year. Good luck, everybody, and we'll see you at this exam, and that will be followed by the final. Good luck.